This is CX1104 Linear Algebra for Computing Chapter 6.3.3. In today's lecture, we'll use MATLAB to get QR decomposition for 4 cases of A, where A has dependent and independent columns. A is tall and skinny, and A is square. We'll only consider 2 common cases. The 2 common cases are that A is a square matrix first, that's the easier one, and the other one is A is tall and skinny. Now, for MATLAB, there are 2 options. One is the economy decomposition, which we have studied in our lectures, and something called a complete or full decomposition. You should read the MATLAB's help manual as well as the NumPy Linear Algebra QR Decomposition help manual. The naming conventions of full and economy is slightly different. In the MATLAB's help manual, you will see that the word economy size is being used, while in the NumPy it is called reduce. So the naming convention of economy size is not the same between MATLAB and Linear Algebra and NumPy. Okay, let's see the help. This is MATLAB. What it says is that if you send a matrix A into a function called QR, you'll receive 2 matrices Q and R, and A is rectangle. You'll produce a upper triangle R, and you will produce a M by M unitary. So the word unitary here is that QTQ equals to I when Q are real. In addition, of course, we have to ensure that A equals to QR. Now, immediately you will see that the first option is the full decomposition, because even though you have M by N, we had expected the Q to be M by N, but here it produces M by M. Alright, now this is what we are more familiar with, which is called the economy decomposition. If M is greater than N, only the first N columns of Q and the first N rows of R are computed. So we are saving computation. Okay, so for example, we have 3 by 2, then so this is M and this is N, then only the first 2 columns of Q are computed. Only the first 2 rows of R are computed. Alright, let's see the following 4 cases. The first case, we have 2 examples. The first example is A square and A has size 3 by 3. The first case is A has independent column. The second case is A has 2 independent columns. The third column is dependent. In the second case, we have tall 3 by 2. And now A has 2 independent columns, and now A has dependent column. That means the second column is dependent on the first column. We want to study the effect of QR on these 4 cases. Now, we are not expecting you to write MATLAB code in the exams. We're just seeing the results here and understanding what MATLAB or what NumPy should produce. Some notation, Q transpose in the MATLAB notation, it is Q prime. So prime is used in place of transpose. Now when A is square and has independent column, then QTQ equals to QQT equals to I. Additionally, R is square and invertible. Let's see whether this is true. So let us give an example of A here. We initialize A, we visualize A, and then to check whether A is invertible or not, we check the rank of A. You have not studied rank yet, just review it. The rank of A tells us how many independent row and column it has. Since this is a square matrix 3 by 3. We hope that the rank will be 3 to be an invertible matrix, and in this case it tells us the rank is 3, and that's great. Alright, we generate the QR decomposition using this MATLAB command. We see the matrix Q and we see the matrix R. So we have a 3 by 3, Q is 3 by 3, R is 3 by 3, R is upper triangle, and not only that, more importantly, the elements of the diagonal is non-zero, so R is invertible. So we check the rank of R is really true, it is invertible, and we want to check that Q transpose Q is equals to I, which is true, and QQ transpose is also equals to I. So this is what we expected, and for sanity check, we multiply Q with R, and we see that the values of QR is the same as what we have assigned, and we are quite happy that we now know that the answer is correct. So this is what we expect for a square matrix that has independent column, so this is quite trivial. Now, what happens when A has dependent column? So let us try a new A. We have this A. So the first column, second column, and third column. You realize that I did nothing but adding the third column. This is the sum of the first two columns. So therefore, the rank of A in this case is 2 as expected, and this is nice. We again do QR decomposition. We get Q and we get R. So now observe that R has a 0 entry along the diagonal. The rank of R is 2 as expected, because it's telling us that although R is a square matrix, its rank is less than 3 in this example, and therefore it is not invertible. What about Q? Q transpose Q? Q transpose Q is still the identity. QQ transpose is still the identity. So the only thing that told us that the original A is not invertible or has dependent column is from the entries of R. We still can get QR equals to A, no problem at all. So the take-home message is that when we are playing with QR decomposition, R is telling us which entries of A or which columns of A are dependent or not by studying elements of R. Okay. So now we switch gear. We can now study when A is tall and skinny. So we now have a rectangle matrix or A, and we still can see QR. Okay. And as a recap, when A is tall and skinny, we'll break Q into two matrices. Q1 will span the column space of A. Q2 will be the perpendicular, will span the perpendicular subspace of A. R1 multiplied by Q1 will give you A, and the subset Q2 will be multiplied by 0, so showing that Q2 does not contribute to A at all. Okay, now let's try. The first thing we try is that we have A that is 3 by 2. A has two independent columns. So we have the first column of A and the second column of A, and these are independent of each other. The full decomposition, Q, we still get 3 by 3. So, sorry, 3 by 3 by 3. A is 3 by 2, Q is 3 by 3, R is 3 by 2. So you realize that only this part contributes to the front part. This is Q1. And the back part is multiplying with this. This is Q2. You can study this very well. The columns of Q2 are orthogonal to these two columns. Okay, let's proceed on to study the properties of Q. Q transpose Q is still the identity matrix. Q times Q transpose is still the identity matrix. What else do we want to get out of this? So on the left, we have the full decomposition of this matrix. On the right, we're going to study the economy decomposition. The economy decomposition, the only difference is here. So observe. The only difference is this command with the parameter set to 0 in QR bracket a comma 0. The second parameter tells MATLAB that we want to perform economy decomposition. So what do we get? Well, we now get Q as 3 by 2. R is 2 by 2. This guy and this guy are the same as Q1 extracted from the full decomposition. The elements of R is exactly the top part of R previously. So the economy decomposition does nothing but saving more computation, showing not what is not required to construct A. What is interesting now is, well, Q transpose Q is a 2 by 3 matrix multiplied by a 3 by 2 matrix. Therefore, it is I as expected. Q transpose is the interesting one, which is 3 by 2 multiplied by 2 by 3. And this is a projection matrix. So you can get this. Let's call this P. And then you can try P square. And then you realize that P square equals to P as what a projection matrix should be. Okay, so please try this at home. And our last example is the tall A, but it has dependent columns. Okay, so a tall A has dependent column. Our A is 3 by 2. So the only way I can get a dependent column is to make the second column dependent on the first one. Let us construct the full decomposition on the left and the economy on the right. The full decomposition, you will get this Q, which is 3 by 3. Get this R, which is 3 by 2. It reveals that there are zeros in the diagonal entries to tell us that the columns of A are dependent. So only this guy is interesting. The first column of A, can you see? Isn't this column vector spans this as well as spans this? Yeah, in fact, they right. Now, what about what do you call that? Economy decomposition. In economy decomposition, when we apply QR with entry 0 here, this guy is still this guy. This guy is still this guy. So there is no change. The economy decomposition is just stopping at the number of columns originally A has. Again, only by studying the entries of R do we know whether A has dependent or independent columns. So that's all we have today. Thank you.